Hello everyone and welcome. My name is Michal and today we'll go through 7 latest questions from the top subject of performance, and all of these have been seen across all EASA authorities in the recent actual real exams. So without any further ado, let's jump into the questions and dive a bit deeper into the questions, answers and the general topics. So for question number 1, what is the definition of wet ice regarding contaminated runways? So unfortunately, when it comes to runway contamination, there isn't no really simple way of remembering them. You simply have to memorize the tables that are given. However, the tip I can give you is that always remember that runway contamination is only reported as affecting your braking performance if it covers at least 25% of the runway. And in practice, the runway contamination will be reported usually by a METAR, ATIS, or the ATC themselves. And then using the runway contamination matrix, which you can see right here, it's taken from ICAO Doc 04041, which is based on ICAO Doc 9881. You can see that according to this runway contamination matrix, you would take then your wet ice, which is right here at the very bottom, and then you can see the runway contamination code, which is then used to calculate your landing or takeoff performance. So this will be the practical application of this. And here also I want to raise your attention to the fact that wet and dry snow will be reported with either up to 3 millimeters of depth for slash dry snow and wet snow, and then more than 3 millimeters of depth. So these are the only ones that are reporting based on the thickness of the layer. So with that in mind, you can see that already we can exclude the first two answers as they are about ice and more or less than 3 millimeters. Ice is not reported based on its depth. And of course, the answers that are remaining, they're both correct. However, one is partially correct because wet ice is ice with a layer of water of any depth on top of it, or ice that is melting. So this makes this answer correct. So now going into question number 2. So if other factors remain constant, how does the retraction of flats and slats affect Vx, which is the speed of best climb, best angle of climb, and Vy, which is our speed for best rate of climb? So generally remember that flaps always degrade your aircraft's performance. They increase the camber of your wing, or in some aircraft even the area of the wing, and so they will increase the lift produced and they will decrease the stall speeds. However, it comes at a cost, and the cost here mainly is a lot of drag. So you will be able to lift off earlier and start your climb earlier. However, once you reach safe speeds, it's always a good idea to clean up the aircraft, because clean aircraft will always climb better and faster. So here also remember the definition of Vx and Vy, and they refer to respectively. Vx will be calculated using your thrust minus drag formula, and then Vy will be based on your power available versus power required. So here remember that if your drag increases with the extension of flats, then also your Vx will decrease, of course, because thrust minus drag, if we increase the drag and thrust stays relatively constant, then the speed will decrease. And the same will happen with Vy, as with more flats we need more power, more thrust, and of course the available one stays relatively constant as we climb. So if we retract the flaps, meaning we put flaps 0, in that case both Vx and Vy will increase. So now for question number 3. During takeoff on a limiting runway, if V1 was used instead of a wet V2, a dry V1 instead of wet V1, due to a wet runway conditions, the result would be. So remember that V1 speed is the decision speed. So this is usually calculated using a comparison of your stop and go speeds. And essentially what it does, if V1 ensures two key things. One, of course, that in case that you abort before that speed, you can safely stop on the runway. And also it ensures that you are able to reach the screen height at your V2 speed, which is at 35 feet, in case one of your engine fails. So these are the two key things, and these essentially ensure that before that speed you can safely stop, and after that speed you can safely also continue and get the aircraft airborne and take the problem into the air. However, the dry V1 versus wet V1, they have exactly the same go speeds. However, the main difference here is the stop speeds, because the aircraft will accelerate relatively the same no matter if the runway is wet or dry, because of course it doesn't use the wheels to accelerate, it uses its engines. So the wet V1 will have the key difference that it will take into account the degraded stopping distance and the braking of the aircraft in case of the runway is contaminated. Meaning that if you use the dry V1, which takes into consideration a better braking action, the accelerate stop distance will exceed the acceleration stop distance available. So the last answer here that can be quite appealing is not correct, because of course the one engine and operative takeoff distance is the same no matter if the runway is made out of pure ice or if it's completely dry. And for the same reason, dry V1 and wet V1 will also not be the same, and the over rotation refers only to your rotation speed, which is calculated separately and is independent of your V1 generally. And now for question number 4. An increase in atmospheric pressure has, among other things, the following consequences on landing performance. So remember that as you increase the atmospheric pressure, it's exactly the same as decreasing your altitude. So this also will be the same if, for example, the temperature decreases. With decreasing temperature, your pressure will increase. So in that case, two things will happen. For the same amount of your calibrated airspeed, you will have a lower true airspeed, and which is good for landing performance, because now your speed over the, in case of no wind conditions, over the ground will be lower for the same calibrated airspeed, but also your engines will be able to suck in more air per volume in case this air is more dense or if the pressure is increased. And that leads us to essentially improved performance in both landing and go around. So that makes a reduced landing distance and improve go around performance. So you can also consider here the use of reverse thrust, which doesn't affect the landing as much, however, it also helps. So in that case, you can see that a reduced landing distance and improved go around performance will be the key consequences of increased atmospheric pressure. However, here I think the examiners want you to know mainly that if the pressure is increased, in that case, your true airspeed is lower as compared to higher pressures with the same CAS, because as you probably know, as you climb with constant calibrated airspeed, then your true airspeed continuously increases. And now for question number 5. So if the headwind increases by 10 knots, the maximum endurance speed will. And this is a very interesting question, and it's easy to fall here into a trap set by the examiners, of course. You need to remember that the endurance is always independent of wind. So you can think about an extreme example, for example, of flying in with 150 knots of the calibrated airspeed in 150 knots of headwind. In that case, you will be stationary over the ground. However, it doesn't really matter what distance you're covering and what speed you're flying at, as you will remain in the air always for the exact amount of time, because the time is doesn't matter how fast or where you're going. And of course, if you are encountering headwind, it's always best to fly slightly faster. However, this is not about endurance. That would be about range and fuel economy. In that case, your endurance speed will always be the same no matter the wind. And this is also true for your speed for the best gradient or rate or angle of climb, as the gradient over or in the air will always be the same no matter the wind. However, it will change over ground, but there's nothing we can do about that, as we care about the speeds and gradients in the air specifically. And over question number 6, so one of the classic questions that you'll see in performance exams, where you need to calculate the runway declared distances. So to determine runway length limited takeoff mass for an unbalanced field, what is the TODA takeoff distance available to be used for Class Alpha aircraft given the following data? So the takeoff distance available is very simple to calculate. Of course, it's always our takeoff run available, which will include, for example, the displaced threshold. And then to this, we add clear rate. In this case, however, it is a bit tricky because the examiners have given us very crazy numbers. Practically, I don't think I have ever seen a stopway being longer than a clear way. However, that is the case here. The stopway, however, is theoretically not included in our takeoff distance available. We use the clearway. So in this case, all you need to do is add tora plus the clearway to get your takeoff distance available. And this gets us to the answer 2,940 meters. Here also remember that your takeoff distance available cannot be more than your takeoff run times 1.5. So in case you have a clearway of 2 kilometers and a tora of 2 kilometers, the takeoff distance would not be 4, it is limited to 3. So 1.5 of your tora. And also for practical reasons, this is an unbalanced field, but in aviation, you'll most likely always use a balanced field, even if it's realistically not very balanced. So what you will do, you will always cut the clearway to the length of the stopway for the ease of calculations. As always, clearway, for the most part, will be longer than the stopway. And this is our final, so question number 7. Which of the following statements is correct regarding the obstacle limited takeoff mask for performance Class A airplane? So here, remember that there are 3 key takeoff masses. So we have a field limited takeoff mass, and then you have the obstacle limited takeoff mass, and lastly the climb limited takeoff mass. So the field limited takeoff mass talks about the length of the runway and whether you can safely take off and reach the screen height. Then of course the obstacle limited takeoff mass, which ensures that you can clear all the obstacles in your path with at least 35 degrees over the net takeoff flight path. So the net takeoff flight path is the gross flight path, which is the average that the authority takes from the test pilots. And then they add 0.8% of margin on top of that for 2-engine aircraft, 0.9% for 3-engine aircraft, and 1% of margin to create a net for 4-engine aircraft. And then lastly, you have the climb limited takeoff mass, and this mass essentially talks about you being able to maintain the published climb gradients for the specific departure with this specific mass. So these masses will be calculated most often by elaborate systems, so you don't have to do it yourself with a piece of paper. However, you need to know what these masses and how they are, what they are, and how they are influenced. And the right answer here would be the 35 feet obstacle clearance in respect to the net takeoff mass, a takeoff flight path. The 50 feet, for example, would be considered for Class Bravo aircraft. And you can also do turns up to 25-degree bank angle rather than 30. So this answers that question. And this will be everything. Thank you so much for joining in. I wish you all the best with your upcoming exams. If you have any questions, always feel free to ask. And I hope to see you during our next video. But until then, have a fantastic rest of your day or week, and bye-bye.